So we're looking more specifically at how to organize and identify a unique address for each electron, and we call that the electron configuration. And we looked at an atom, and if we looked at this as the nucleus of the atom with energy levels moving out, we realized they don't just exist a certain energy level away from the nucleus, they also are moving in certain patterns, okay? And we call those patterns orbitals. In the first energy level, we have what's called the s orbital up here. We know that the s orbital can hold a total of 2 electrons. In the next energy level, we have s orbitals, but we also have p orbitals. P orbitals can hold a total of 6 electrons. And in the next energy level, what up here are these d orbitals, and d orbitals can hold a total of 10 electrons. Think of these as different sized houses. So an S house can hold 2 people, a P house can hold 6 people, and a D house can hold 10 people. We also have the F orbital, but we talked about how the lengthenide and actinide series, which is where those F orbitals exist, really isn't something we're going to address that much this year. So rather than think of them as houses, think of them as probabilities of distribution. So the farther we get away from the nucleus, the greater the probability of the electrons assuming a larger space. If they're bees buzzing around a hive, they're going to buzz in different shapes, and those shapes have recognizable patterns. So let's look at how to write these electron configurations. Think of the electron configuration as just the address for every electron in an atom. And we have these things called blocks. So the first block that we talked about in class is the S block. This is the S block. What that means is the very last electron in all of these atoms, the last electrons, exists in an S block. There are P and D electrons, perhaps, but the very last ones exist in an S block. The transition metals here in the middle, the very last electrons in those atoms live in D blocks or D orbitals, and the very last electrons in these nonmetals and semimetals or metalloids exist in P. This is the F. We're not going to worry about that. Then the energy levels we can see down the side. So that's n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. So the very last electrons, let's say in francium, exist in the 7th energy level, and the very last electrons in lithium exist in the 2nd energy level. So we could say that, for example, the very last electrons in strontium exist in the 5th energy level, or 5th layer away from the nucleus, and they are conforming to this S distribution. Now the D block is a little bit weird. The energy levels lag behind. So that would be 3, that would be 4, 5. And they pick back up when we get over here to the P. So if we were to give the electron configuration, let's say for manganese, we would just count all the way through. And by the way, this is S. So you go 1, 2, 3, and by the way, I'm sorry, this picks back up here. So 1, 2, 3, 3, 4, 3, 4, etc. So we'd also go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Now we want to end on manganese, so it would be 1s, 2s, 2p, 3s, 3p, 4s, 3d, but we want to indicate that that's in the 4th subshell of the d orbital. So we want to indicate the total electrons. So 1s2 would take us to here. That's the first energy level, the s orbital, and the 2nd electron. 2s2, 2nd energy level, s orbital, 2nd electron. And now when you move into a new orbital, you restate the energy level. So 2p, we got to go all the way through. 1, 2, 3, 4, 5, 6. 3s, 2, and then 3p6. Gonna move down here. 4s2, and then they'll be thrown off here. 3D, and then we count to where we get 1, 2, 3, 4, 5. So no other electron in the manganese atom has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Okay, so that gives us the total electron configuration of the manganese atom. Okay? That tells us where all the electrons are, and the last electrons existing in that 3d5 area. Sometimes there's a shortcut where you just start at the most nearest noble gas. So we could say argon, because this is essentially the electron configuration for argon, 4s2,